лекции по ВПП оптимизации, они тоже есть в открытом доступе. Они устроены как бы из двух частей, такая теоретическая строгая часть и другая, то, что рассказывается на лекции непосредственно, примеры, приложения, пояснения, так сказать, содержательное. Вот это замечательный такой образец лекций. Теперь Стивен только что вернулся из Нижнего Новгорода, где происходила конференция, ифаковская конференция, что-то education или чего-то такого.
Advanced Control Education.
Advanced Control Education. И там, в общем, была и для этой конференции Стефан подготовил такой обзорный доклад про Ляпунова и его идеи. И вот как он мне сказал, у него не было впечатления, что там этот доклад восприняли. И поэтому он его как бы повторит в сокращенном виде здесь, потому что это как раз та аудитория, где такой доклад будет действительно понял и воспринят. Окей, sorry. But it's nothing bad.
Okay. Thank you for the introduction. I think. I don't know. But I'm sure it was horribly exaggerated, so you shouldn't believe it. I don't know what Boris said, but I'm sure it's exaggerated. Okay, so what I'm going to do is, I know it's late, so this is a talk I gave in Nizhny Novgorod, except I think I can go very fast over it, and anyway, it's mostly just ideas. So, and you have to tell me if I'm going too fast, English or anything else. You can make answers.
В любом месте, говорит, что непонятно. Говорит по-русски непонятно. Непонятно means we don't understand.
Perfect. Good. Okay. Okay. So actually it's a historical lecture, and it's about how the idea of Ляпунов's ideas stretch from 120 years the whole way. So mostly it's about ideas, and it's not. There'll be a couple of examples that are very specific. That's when the math will come. But until then, just ideas. Okay. So what we're going to look at is we even go back before Ляпунов and look at. Oh, I should warn you. I will mispronounce all Russian names. So I apologize now.
Ляпунов is okay.
No, because we say Ляпунов. That's not right. I know it's not right, but that's what we say. So I'm sorry. You'll have to translate that yourself. Okay. So, all right. So I'll go back even before. I'll look at the precursors and the idea of conserved and dissipated quantities. I'll look at Ляпунов's methods, but very high level, no details, and I want to make some points there. And then I'm going to go very fast over convex optimization because I assume here everyone knows about this. So I'll go very fast over that. And then we'll just look at two examples that I made up. Actually, I just made them up last week. I was in Turkey on a boat in the Mediterranean, and I just typed them into my laptop, and we'll take a look at those. So we start with the background, so conserved and dissipated quantities. I'll go very fast. So you have a dynamical system, and you have some function, scalar value. And you say that it's conserved, or an integral of the motion, or an invariant, if it's constant along trajectories. Okay, so this is maybe early 19th century idea. It's from physics. Examples would be things like total energy, total angular momentum, total amount of fluid in the system. And of course, if something's conserved, then it says that the trajectories stay in the level sets. Right? So if you have planetary motion, they stay in the level sets of total energy or something. Okay. The next step is to go to inequalities, and this is a theme. You go from the equality, you relax to an inequality. So here, all you do is you have an inequality here where you had an equals, right? And this is still, I guess, an idea sort of from physics, right? So this is a dissipated quantity. And an example would be an energy system, the energy of a system that has a loss mechanism, right? Like a mechanical system with some loss, or electrical circuit with some resistors or something. Okay, and this is the idea. And then it says that it's kind of, this is obvious, if you have a dissipated quantity, then all the trajectories stay in the sublevel sets. And for example, if the sublevel sets are bounded, that immediately implies the trajectories are bounded. So you immediately see this idea that if you know something about some function v, for example, the sublevel sets are bounded, and this expression is less than or equal to 0, then the trajectories are bounded. And now we get to Ляпунова. So, and the year is 1892. So, as far as I can tell, I believe this is the main point. I'll say more about it. And we don't think about it because I was taught Ляпунова theory, you were taught it, and you don't think about it. But in something like 1892, this is a radical idea, right? If you look at these ideas like conserved quantity, dissipated quantity, they're not things you make up. They're things like the energy or the total momentum or something like that, right? This is a radical idea. It doesn't have to come from physics. In fact, even more radical is the idea. It said, let's search for a function that establishes some property, like boundedness of trajectories, right? So this is the idea. I mean, so now we don't even think about this anymore, but if you think about it then, from what people knew, this was a radical idea. Well, in fact, it's very strange, right? Someone in physics wouldn't think of this, right? And the idea is, of course, you're going to use a function like this to establish some property of a trajectory. And the classic example is if you find v with bounded sublevel sets and v less than 0, v dot, then all trajectories are bounded. I mean, this is kind of standard. Okay, but actually, this is a very important point, and I think it's not appreciated enough, not even close, in my opinion. When you see people teaching Ляпунова function or writing about it, it's all about stability, right? And the title of your first book on this was something on problems on the stability of motion, right? So it's all about stability. So my claim is, number one, radical claim, stability is completely uninteresting in practice. It has no interest whatsoever. It's of no interest. It's totally useless. It means it's meaningless. Okay? So the correct thing to say about, a system that is unstable, like a control system, it's not that it's unstable. It doesn't work. That's a much stronger statement. To say, so it's not like it's not stable. So I don't know why people are still focusing on stability. I don't understand it. It makes, of course it's important to have it.
Just tradition.
It's tradition. It's cultural and historical tradition, right? So, but the point is, you can use, that's not useful. A useful thing is quantitative. It's quantitative. So quantitative is to say, if you run this flight control system on this airplane, running at Mach 0.81 at 33,000 feet, and there's a downdraft like this, here is a useful statement, that it will not drop more than 50 meters before going back up to the height. That's number one. In 12.3 seconds, it will be no more than 30 meters under where it's supposed to be. That is a useful statement. To say the control system is stable is totally useless and uninteresting. This is my claim. Okay? Actually, it's not my claim. It's correct. So, it's not, okay.
So theorem number one is any your claim is correct.
No, that's not true. Later I'll tell you where it's a claim, but it may or may not be correct. Even sometimes it's a claim of mine and it's false. Okay, so the point is that you can actually use this idea of Ляпунова for many other things. You can bound performance indices. You can do things like estimate or bound growth rates and Ляпунov exponents. You can handle uncertain dynamics. I think everyone here knows this. Stochastic systems, even systems with time delay, reachability. We saw a talk on it earlier today, and in fact I was going to ask, I can't remember who gave the talk, I was going to ask about that sometime. Okay, now you can do all sorts of stuff. You can even do state feedback synthesis. and things like that. So there are many things you can do just with this one very simple idea. And I'll show you an example of stochastic control as well. So, and that spans all the way to 2012. So that's a full 120 years. Okay, so that's actually my first claim, is that Lyapunov's idea, it should not be stuck in this historical prison where all it's used for is stability. This is not interesting. It's actually unbelievably useful right now for real things. Actually, there's one more ingredient you have to add to it, which we're going to get to in a minute. So, of course, the big question on Lyapunov, when you teach it, when you're learning it, you should ask this question immediately. People say, well, if there's a V that does this and this and this, then this holds. And of course, after a while, you should ask the question, where does this V come from? Right? That's the big question. So first of all, for things like linear dynamics and quadratic cost, there's analytical methods. And, I mean, you know, usually you solve linear equations or something like this. And these are typically sharp, meaning that if you're bounding a quantity, the zero gap, right? If you're estimating a performance number, if it's a qualitative thing like stability, it's necessary and sufficient, right? So a linear dynamical system is stable if and only if there's a quadratic Lyapunov function which proves it, right? So, okay. Now the traditional sources are, well, the funny part is like physics, right? So it comes back from physics. So you could use things like kinetic plus potential energy, and this would come up in passivity or something. You could use the exact Lyapunov function for a related linear system, and his original, the original 1890 results were this, right? It tells you about linearization or something like that, linearized systems. And in fact, it turned out later that very sophisticated things like Popov criterion, circle criterion, Zipkin criterion, every single one relates to a Lyapunov function. All of those are simply methods for finding a Lyapunov function. They're very non-standard. It's not totally easy to see what it's doing, but it is doing nothing more. And in fact, it's pretty much true that almost all methods for stability analysis and things like that, they all just reduce to Lyapunov methods. All of them. And including ones where it's not obvious, like this. Like, how is the Popov criterion? Okay. So how do you find V? Well, in 1890, and in fact, all the way to the present, because the way people teach these things is as if it's still 1890. So the way it works is something like this. You choose a form of V, like quadratic, and you call that a Lyapunov function candidate. And then the idea is, the next step is you find values of the parameters for which required properties hold. 1890, all the way up to 1945, something like this. This is done by hand. And that means, you know, you take a three-state system and you sit there with algebra and pencil and paper and you work out inequalities and you show if some inequalities hold on some parameters, the following holds or something, right? So that's the traditional method. And here's my claim. Here's the modern method. Here's the new ingredient. It's not new. Here's the ingredient you add. Two ingredients, you add them together. It's this, and it looks very simple. It looks just like Lyapunov's original approach, right? It looks like this. You choose a linear parameterized Lyapunov function candidate, like quadratic. And then you find values of parameters which require properties. So except here's the point. You use convex optimization, and that's numerical. Okay? So, and this was first proposed in complete clarity by Katniss and Skordinsky. Right? So, but I mean, the ideas were, you could probably trace earlier. Okay? So this is like early 80s or something, but probably people knew earlier. 80s. So, and so actually, if you look at this and you look at this and look at them long enough, what's shocking is how close they are to each other. And so my claim is the following, that, in fact, if we were to resurrect Lyapunov and explain what convex optimization is, and show him this, he would, not only would he understand it immediately, but he would have approved, I think. I mean, I assume. Well, anyway, we don't know. By the way, that statement is not true. We don't know. That's still a conjecture. That's conjecture, okay? So that's my claim. Okay. All right, so how do you find V via convex optimization? Well, this is a huge field, so I'm only going to just give you the flavor of it. So, well, this is just to give you the idea of how this might work, right? So, oh, I should say one big thing. There's a huge difference between this method and this method. Even though they look the same, huge difference. The difference is this. This is limited to like second order, third order, fourth order systems, or silly systems where you can draw a circle on some plot and, see if something happens, like a pop-off criterion. Very specialized problems. This is extremely expressive, right? You can handle large-scale things, an infinite variety of problems, right? Problems involving not just stability, right? But things like performance bounds and things like that. It's almost the level, the amount, how expressive it is vast compared to this original method. But the idea is exactly the same. Okay, so for quadratic, it turns out a lot of things come down to matrix inequalities, or LMIs, or something like this. And so, for example, when are the sublevel sets bounded? Well, that's when P is positive definite. All of these properties, they are, in fact, generically, they're convex in the parameter P. Okay? Now, they may be hard to express or hard to handle, but they are always convex. Because they're statements actually, they're inequalities that have to hold over all of state space. And they're actually, at any point in state space, they're linear inequalities in the parameters. So these are, generically, they're all convex. Okay? And what that says is that searching for a ल्याpunov function is a convex optimization problem. And then that means it's readily solved numerically. Okay? Now, by the way, this is a lie, of course, but it's okay to say it, right? So it's because it doesn't. I mean, there's lots of convex problems that are too hard to solve. But anyway, it doesn't matter. We move on. Okay. So I'm not going to talk about this, but if you learned about this material, and I assume you actually already have learned, because as you'll figure out pretty soon, you'll figure out that essentially all of this came from, well, first Russia, then Soviet Union, then Russia again. So, no, then I guess we have to say Ukraine. Okay, well, we'll get it. Okay. So in the 1940s, Luria, others, and this just means there's many, many others, and I just don't feel like listing these. Came up with the S procedure. And this is a variation on duality. In fact, it's nothing but duality, in fact. And it's a method to verify a quadratic inequality on a set defined by quadratics. And it's a very simple condition. It looks so simple that when you see it, you think, that is so simple-minded, nothing good can happen. But it turns out this is enough to establish essentially all nonlinear stability theory. All of it. So things that people are celebrating, the celebrated circle criterion, is absolutely nothing but S procedure, quadratic Lyapunov function, Lyapunov's ideas. It's nothing more. Okay, so I'm not going to talk about that. There are other variations. For example, why do you end up focusing on quadratic functions? And the reason is very simple. It turns out that if you think about it, what you have to do if you're playing the Lyapunov game is you have to establish an inequality holds on Rn. Right? Well, in fact, that's impossible in general. I mean, if n is 2 or 3, you just grid and you go to lunch and you have a computer, you kind of look around at all the points and it's done. But if it's 10, you cannot do it. There's just no way you can do it in R10. Right? So there are exceptions, and the most obvious exception is a quadratic function. So for a quadratic function, I can check positivity, I can check an inequality, and for example, in R10, I can do it in, does anyone know? How long does it take to verify positivity of a quadratic function on R10? On my laptop. We're gonna have lots of discussions.
Bytes.
What?
Bytes.
I wonder how long does it take?
Depends on the dimension.
10. I said 10.
Nanosecond.
What?
1 nanosecond.
A nanosecond. You ruin every. That's not. You're supposed to say a second or something. Then I can say you're way off. So it's under a millisecond. But see, now you ruined it because now it sounds long and totally ruined the whole story. That's okay. All right. All right. So the modern, there's a step beyond quadratic is you can handle higher order polynomials, for example. And it turns out every single one of these, they all reduce. So quartics, right? So how do you verify if a quartic is non-negative, or one quartic is less than another quartic? Well, it turns out these all reduce to LMIs and to semi-definite programming. So it's all tractable convex optimization. So I won't say anything more about that. Okay. And this I'm actually gonna go fast enough because I think everyone here knows all of this, and I'll just skip it. You can look at it if you like. I will say a little bit about modeling languages, and I know you've seen this, and it's an interesting thing. The idea is you have a high-level language that supports convex optimization, and it does so through, in fact, what it does is it formalizes convex analysis. In fact, exactly 2 rules of convex, and only 2 rules of convex analysis. And what it allows you to do is to write a convex optimization problem in a natural way. And the idea is to make the source code look like the mathematics. That's the goal, right? And you can do this. And it turns out this allows you to do rapid prototyping. It's ideal for teaching. I mean, because it means it's not a big load. I mean, to tell us you can have homework problems and have people solve very sophisticated things. They write a script, it's 10 lines. Right? So it's actually great for that. Okay, CBX, I know many of you know about this, but it's a parser solver, and I mean, just to give you an example, here would be some convex optimization problem you might want to solve. This might come up in machine learning. Actually, this is totally made up.
I have a question.
Yeah.
Language questions.
Yeah.
What's the fundamental difference between parser and solver?
Oh, so a parser merely looks at something like this and makes a tree. It understands what each part is. It, for example, realizes that's a constant matrix, that's a variable. It makes the tree. It does the symbolic analysis. A solver solves a convex optimization problem. A numerical instance. Yeah. So we'll talk about
it. Kind of decoder.
What's that?
It's this kind of decoder.
The parser would be like a decoder. Yeah. So this is a convex optimization problem. So you would write the source this way, and this would just run if you type this in. And the idea is to make the math look like the source. And in fact, in this case, the source is clearer than the math, in fact. Because in math, we're sloppy. Up here, for example, it's kind of a convention. I didn't say that x was the variable. That's just a convention. Okay? So, whereas here, of course, you have to think better. So this is the idea. Okay. Now we're going to do just 2 examples. And just to show you what you can do. And the idea is, what can you do if you take the ideas of Ляпунова and you connect them to just convex optimization, basic convex optimization. And then it's not part of the basic idea, but the idea is if you have a parser solver, it's not just what can you do by putting these 2 things together, but what can you do in like 5 minutes floating on a boat in Turkey with your laptop. Okay? So this is the idea is you can do a lot very quickly with these ideas. So here's one. And it was easier for me to work all of this out from scratch instead of even looking at papers or things like that. It was easier just to do it for myself in the beginning. So, all right. So now we'll look at some examples. So now you can turn on your math mode. I have just a time-varying linear system like this, and this matrix A can have any of these k values here. Okay. And I have a quadratic sum performance index, very standard, Q's positive semi-definite. And of course, this could be plus infinity. That's possible. Right? So, now this depends on the particular sequence of A's. So it depends what it is. And so we're going to take the worst case performance index. That's the supremum of J over all possible sequences. Right? So it's simple enough. Right? And not only is it simple enough, but you can immediately imagine very practical uses of this, right? Because you have a system, because it turns out actually if the worst case performance index is less than some number. It's the same worst case performance index if A of t, if AT is in the convex hull of this. And that's very interesting because that means this could be a nonlinear system, and you could actually establish stability of a nonlinear system, an adversarial system, all sorts of stuff. So I won't go into this, but it should be clear. This is not just, this is very close to something very practical. Okay. Now, when you have just one of these, well, that goes back to 1892, right? That's this. If it's just one linear system, I mean, it doesn't matter, but you always start from this, the one linear system, right? So you start with one, and you just solve a set of linear equations, right? Q is given, A is given, that's a set of linear equations in P, you solve them. If P has a negative eigenvalue, J is plus infinity. Otherwise, J is x0 transpose P x0, period. Right? So, and then you just kind of memorize what this looks like. I mean, you know what this looks like, right? So now let's see. Now let's see how if you take the idea of ल्याпунова, what happens. Well, you do this. If you could find a function v, which is non-negative, and has the following property, that it reduces by x transpose qx for any of these dynamics matrices. If you can find such a v, then the following is true. It says that along every trajectory, v goes down by at least this amount. And so that says that this is true. I mean, you just iterate this inequality. This thing is you can remove this because this is non-negative, right? And you immediately get this. And by the way, I mean, notice that the argument is completely elementary. There's nothing sophisticated about it. It's algebra. Right? So this is very common for ल्याпунова theory. That when you actually write, when you look at the essence of the argument, it's completely trivial. As it is here, it's completely trivial. Okay, well that says that if I can find a function that satisfies this, and by the way, this inequality has to hold for every x. Okay, so we're back to this question of when does an inequality hold in all of Rn, right? That's the question. So then you would get this, and then, this you can immediately see that the set of v's that satisfy this is a convex set. I mean, it's infinite dimensional, but it's convex. Because this is an inequality, linear inequality in V for each x, right? Okay. So what you should do is minimize this over all V's that satisfy that and that. Okay? That's an infinite dimensional convex optimization problem. And by the way, if you solve that infinite dimensional problem, you will get the exact answer. You get J worst case. Okay? So there's zero gap in this case. Zero. Okay. I mean, that's kind of a theoretical question. I mean, because who cares if it's sharp? Because you can't search over all these. Okay. So let's just, to see how this works, let's take a quadratic ल्याпунова function candidate, like this. And those inequalities now reduce to matrix inequalities. And this is, again, I mean, I just mentioned it, everyone here knows this. But the point is that the most common tractable case when you can verify an inequality in Rn, R10, right? You can verify any inequality in R3 by programming it and going to lunch, right? In R2 by programming it and having a coffee, okay? So, yeah, but this doesn't scale well, right? So, R10, forget it, except for quadratics. That's the exception. Okay. So this is the set of linear matrix inequalities, right? That's a matrix, an inequality in P, that's the variable. And you should minimize this thing. And the interpretation is extremely simple, right? You're finding what is the best upper bound on the worst case performance that you can prove using a quadratic ल्याпунова function. Okay? So that's it. Yeah.
The P will be x0 dependent anyway. Can you somehow come up with it?
Yeah, no, it will. Yes, it will be x0 dependent, that's correct.
No way to avoid this.
Well, we can make another problem if you like. I mean,
J kind of universal P.
Yeah, no problem. You could do something like this. You could say that I don't know what x0 is, but it lies in this ellipsoid. And find me the worst case. Find me the worst case.
No, in Rn.
What?
In Rn.
No, then it's plus infinity. Then I can answer the question right now. It's plus infinity. Right? Because it's quadratic. So if you don't bound x0, it's plus, you don't need LMIs. It's plus infinity is the answer. Right? Look,
yeah, we
of
should
course,
take it
it's quadratic.
on a ball.
It has to be on some bounded set. Yeah. So So you could do anything. We could say put it on the box. You could make it stochastic. You could say it's a random variable. We could do every one of these, right? You could say the coefficients are anything. Okay, but you're right. P, of course, because of this, P will be dependent on x0. Absolutely. Okay, so here's the cool thing. So when people first started fiddling around with LMIs like this, you could look at this and you could go around and everyone, you could, congratulate yourself for finding an LMI thing, but it was a huge pain in the ass to actually do this, right? Now, fortunately, if you stick to like theoretical style and you don't have to show, you don't have to actually try it or anything like that, then there's no harm. You don't have to do anything. But if you actually want to do it, it was a huge pain. But look at this. You see, here's the map. Here's the source code. It's completely, they're identical. Actually, this is clear. So that's the executable source code. Okay, completely clear. Well, what happens is when CVX parses this, it creates a large semi-definite program when that's solved. Right? But that's all done automatically, and actually because the parsing is done using an extremely small core set of mathematics, the parser, I believe, is correct. Right? So it's it's like Linux. Linux works because it's small and it's designed by intelligent people. Right? Windows is the opposite. It's the exact opposite. Right? So, okay. All right. So now I want to point something else out. So that now you can do worst case performance math. But now I want to show you something. Here's another example, same example, but it's an example of a non-traditional use of Lyapunov's methods, right? And even he would probably be a little uncomfortable. No, not really. Okay. So and by the way, people don't teach this. You know why you don't teach it? Because you can't prove anything about this. Right? And therefore, it doesn't fit with this theoretical style of work, right? It's extremely useful in practice. So here's what it is. Let's suppose you want to do worst case simulation, right? And I think people have even shown for this problem, computing the worst sequence is like NP-hard or something. I don't know. You can ask your, he'll know. Okay? But let's forget all that and let's go ahead and do some worst case simulation. I mean, so you can do lots of things. You could, for example, make simulations where the A was chosen randomly, right? But that'll do badly, but it won't be anything close to the worst. So here's a perfectly good thing to do. Makes perfect sense. What you do is you find the V that proves the best bound. Okay? Then this V should be close to the true V, which you don't know and cannot represent. And then what you do is this. You simply you greedily choose which A increases or decreases the Lyapunov function as little as possible. Okay? It turns out this thing works unbelievably well. I mean, it's a way to very quickly get something that's bad. And so if you're actually doing this in practice, this is a wonderful thing to do, right? And by the way, because you now have an up bound, which is absolutely provable, and you have a lower bound, you now have a gap, meaning a difference between them. And if they're small enough, you're done. Hey, there's no reason. And look, the reason this would get no respect from people who do too much theory, I can tell you why. Because you would say this, and then people would look very uncomfortable and say, how big is the gap? And I would say, well, it's not negative. That's actually true. That's a true statement. And then they would say, well, what else can you say about it? And the answer is basically nothing. Absolutely nothing. Right? So, I mean, look, in some special cases you could. But in fact, what you could say about it would be so useless in practice, it wouldn't even be fun. Yeah, you'd have some stupid thing like, oh, the gap is less than, square root k log k times k. I don't know what, you know these things. You know these things. You've seen this, right? By the way, if you think I'm making fun of the classes you took, you're right. Yeah, so, okay. So, all right. Okay, let's just do, I just totally random numerical example. I just made one up. I took this, and it's a good example actually, because there'd be two other ways where I would have had to find another seed or something, but I wouldn't do that. I ran it. I ran a code that was a script that was about 10 lines long, no more. It was what you just saw. I ran that script, And you get an upper bound, which is 25. And you get the lower bound from approximate worst case is 16. And so we know now that the worst case objective is between 16 and 20. That's kind of crappy, right? That's like a, I don't know, what, a 50%, 30% gap. But the truth is these are quadratic performance indexes, so you should take the square root to get the right, you know, that makes sense. All of a sudden now, instead of being 30%, it's a 15% gap, right? So that's not so bad. And then you have to accept the following. That we have to understand, where does the Q come from? And in fact, in all of control, where does Q and R come from? So where do Q and R come from in control? That's the right answer. It's like you just, like, the answer is they're made up. They're totally made up, right? So the point is, if you're within 15% in something which was totally made up in the first place, then from a practical point of view, it's done. If someone says, oh, that's terrible, a 15% duality gap, oh, terrible, you'd have to make them, they would have to justify that their Q has meaning at the second digit, which is false, because the way people in control, Q, you just make up Q, and they're usually diagonal, and then what you do is, this control signal is too big, so you increase that R, that diagonal entry in R. This is how it works. These things are not big. Okay, I won't move on. Oh, by the way, I happen to know what the actual answer is. If you run a more sophisticated upper bound, it went down to 17. Okay, so in this case, there is, from a practical point of view, 0 duality gap. And what I do is when I give talks on these kinds of things, I actually, even 17 and 16, I simply say it's a 0 duality gap to irritate people. It works. People say, that's not 0, and I go, oh wait, no, that's 0. And I say, in practice. So, it works. Okay, fine. Okay, so this is what I did to get a better one. Okay, so now we look at the second example. This one is more sophisticated. Okay, and this one actually, in my opinion, is extremely useful. So you should all listen very carefully. Right? And this is, in the last couple of years and things like that. Okay, here it is. So I just quickly review stochastic control, which I assume you all know anyway. So you have a nonlinear dynamical system, a state, an input, some kind of randomness or process noise. I just make these IID and independent of x0. We're going to look for state feedback policy, mu, and we have a stage cost function, and then this is the average stage cost. And the stochastic control problem is to find this function, mu, that minimizes this thing. Okay, so that's stochastic control. Right? It's a simplified version, but that's it. And it's not an optimization problem, or if it is, it's a very sophisticated one, because infinite dimensional, you're actually optimizing over functions. Right? So that's it. All right. So here's the classical dynamic programming solution. It says the following. It says, look for a function v, interestingly named, but so look for a function v, and a number alpha that satisfies this. This is the Bellman operator, and it maps a function f into a new function on the state space. And it says you take the expected value of v at the next step. It's random, the expectation is over w, t. And to that you add the stage cost, and then you minimize over u. Okay? So, and then you look for a fixed point of this equation with this offset. Okay? And if you find this, then the optimal policy, I'll be done in 5 minutes.
No, that's okay.
Okay. And the optimal policy is simply the argument here. And this is so I assume everyone has seen this. Okay. Now, this is really just a solution in principle only, because there's only a few cases where you can really do this, right? And the few cases, you can name them. It's like, when you talk about solving differential equations, right? You take a class, and the class goes through, they show you some linear differential equations, a couple of quadratic ones. Basically, the point in that class when you teach it is the class should finish before the truth is revealed. The truth is there's only 17 differential equations you can solve analytically, right? And so, by the way, if any of you are teaching this class, don't go fast, because this is a disaster if you go too fast, and then you have to reveal the truth to them, which is good. Anyway, it's stupid and it's irrelevant, right? These 17 ones that you can do analytically, because in fact, differential equations are no problem. You just solve them all numerically. Okay. Oh, the famous and useful exception is this. If f is affine and v is quadratic, this is a beautiful thing. So convex quadratics play nice with Bellman and dynamic programming. Play nice means this. Convex quadratics are closed under precomposition with an affine function. That's fact number 1. Fact number 2, they're closed under expectation, sum, and they're closed under partial minimization. If you have a convex quadratic function and you minimize over some of the variables, the result is a convex quadratic in the remaining variables. It's sure complement, except quadratics could have a linear term there, right? And I assume everyone knows this. But the point is, because of those 3 properties, it says that the Bellman operator preserves convex quadratics. It maps convex quadratics to convex quadratics, and that's what makes this actually actionable in the case of convex quadratics. So you get this is not just a fake theoretical. I mean, it's very interesting, right? That this is the structure of the control of the optimal control. For convex quadratics, you can do everything perfect, exactly. Okay. So here's ADP. It's approximate dynamic programming, and I guess have people seen this? No. See? Okay. Well, see, it's theoretical snobbery again. Okay. So this is. I'm going to tell you something. I'll tell you a dirty secret about this too. Okay. So here's approximate dynamic programming. Instead of the true value function, which you can't compute, you can't even represent it, so don't even try. Right? So instead, you plug in some other function here. All right? And you want to choose this function so that, now to evaluate the policy, you have to solve an optimization problem every step. So you choose this in such a way that this is easy to solve. It could be a convex optimization problem, for example. And I'll talk about that tomorrow morning. Right? So, or it could be something easier, we'll see. Okay, so this is this. And the other thing is, you kind of want this to approximate the true one. And so this is the idea. Okay, so this is, and now, so here's kind of if there was an executive summary of control in the year 1905, it would be something like this. That PID control works unreasonably well. Right? There's no reason something this simple should work on all sorts of things, right? It's ridiculous, in fact, right? Everybody agree with what I'm saying? So that's the idea. Okay. So my claim is, here's a secret. Here's this from 2005 instead of 1905. This works unbelievably well, even when the ADP, is a really crappy approximation of V. Now, don't tell anyone this, okay? Because, right? And of course, you'll get zero respect from theorists because they'll say, well, what can you prove? And there are people who prove things here, and they're stupid. They're things like, this is off by n log n, which is totally useless. So, by the way, this means if you need to do control, I would do nothing but this. For me personally, I would do no control other than that. And your entire job is merely to figure out something there, but it does not have to be a good approximation of V for this to work well. Right? So that's, now you know a secret. A very useful secret. Okay. Now, of course, when you do this, you simulate it by Monte Carlo, and then you figure, you get and you want to know how suboptimal is it, right? You build something, it's for supply chain or finance or traditional control, you simulate it, and then it works pretty well. And you say, well, how, are you 5% suboptimal, 10, 20, factor of 5? You don't know, no one knows. Now, in many cases, you don't care. But I'll show you what we're going to do. We're going to, now, Mr. Ляпунова comes in. Okay? And in fact, this is exactly the idea from 1892. There's the Bellman equation. It's an equality, right? It says it's a fixed point of the Bellman operator. That's the Bellman equation. All we're going to do is this. We're going to go over here. We're going to relax that equality to an inequality. And this is the Bellman inequality. Okay? So that's it. Right? And now if you take a look at it, it turns out you can show various things. The Bellman operator is a monotone operator. Right? Not a monotone operator like a monotone operator, but it's meaning if something is pointwise less than something else, the Bellman operators are. Right? And in this case, actually, if you take a look at this, you can reveal, you can see immediately, this is convex in V. Right? Why? Because to say that this is less than or equal to the min just says that this is true for all u in here. So you don't need this min, you just write for all x and for all u. It's a set of inequalities. They're linear inequalities for each x, for each state action pair. It's a linear inequality. This thing is convex, the Bellman inequality, always, generically. Right? Okay. Now, it turns out, if V satisfies the Bellman inequality, then it turns out alpha is a lower bound on the optimal cost of that stochastic control problem. Okay? And so the obvious thing to do is you maximize alpha, subject to this inequality. That's convex optimization always. Always. Right? It may not be tractable in general, but it's always convex optimization. Okay. And you get a performance bound, but here's the cool thing. You solve this problem, and it should be completely obvious by now, right? If you kind of get into the spirit of this kind of broadly interpreted Ляпунова idea. You maximize alpha subject to this, and that gives you a bound on the optimal performance, right? And that's not the heuristic. I mean, that's whatever that number is, it's absolutely a bound on how well anybody can do with any policy. But at the same time, you get an actual V. And that V is an amazingly good candidate for ADP. Makes perfect sense, right? So, actually, you know what? This is the same as that time-varying system we just did. It's the same story. Okay, so now we do a numerical instance. And this one is crazy. It even shocks me. So here it is. We have a linear dynamics. It's completely standard. W0 mean and covariance W. The cost is absolutely standard LQR. Okay? Here's the difference. The inputs here are restricted to have a finite number of values. So that's it. We can only have a finite number of values. Right. So, oh, by the way, we can get one very good. We can get a bound immediately, which is that the LQR. If you remove this constraint, then this is a pure LQR problem, and we get an LQR cost, and that's obviously a lower bound. Okay. Okay. Now, when you instantiate this with a quadratic Ляпунова function, you get this. Quadratic Bellman function, but it's the same thing. The inequality turns into this. This is the expected value of V at the next step, but you know the W0 mean, so all the cross terms cancel, and the W only comes in here. And so this holds for all x and all u, if and only if this inequality holds for all u. That's finite. So this is just a set of LMIs. Okay? And you maximize alpha. Right? Nothing is complicated here. Nothing. And this is all completely trivial. Right? I mean, nothing is complicated. Right? And this is high school, right? It's when is a quadratic function non-negative? Right? Okay. So there's the code. And that's literally the code that runs. So it's completely clear, very simple. That's it. It's literally that long. That's how long it is. This is already doing something very sophisticated. This short little snippet of code takes a few minutes to type in. Is actually going to produce a number, which is a lower bound. It's an absolutely solid, provable lower bound on the performance of a stochastic control system over all possible policies, over this infinite dimensional set of policies, right? I mean, it's worthwhile to stop and to think of how sophisticated what this computation is that's going to do. Okay, so you solve this, and then you can use ADP. But oh, ADP is trivial. ADP is this. You find a quadratic value, approximate value function, and then your control is just argmin of g of x, u, plus, there's a finite number of u's, so you just check them all. Okay. Here's a numerical example. It's got 10 states, 3 inputs, and 10 input values. By the way, this is severely quantized. Right? If you have 3 inputs, and you only have 3 values per input, that would be 27. So if you take the cube root of 10, that's what? 2. Basically, it's 2. So that says, this is how severely quantized you are. You have 3 different actuators, and for each one you have like 2 choices, a little bit more. Everybody see what I'm saying? This is severely quantized. All right. Just type in random data. The LQR cost is like 42.5. Okay? So the cost here, it could be plus infinity. right? It wasn't. The lower bound is 68.1. Okay? It makes sense. But actually, this is shocking. I mean, that's kind of weird, right? That it would only go up that little. Oh, by the way, the true cost could still be plus infinity, right? Because that's a lower bound. And 68.1 is a lower bound on plus infinity, right? So that one was true, by the way. That statement is true. Okay. All right. So if you run ADP, you get that. Okay. And what this is a controller. And oh, by the way, the funny part is this one is actually true, and this one is not quite true. Anyone know why that's not quite true? Or there's at least there's an asterisk here and a little footnote. What is suspect about this? What? This can be verified in infinite precision arithmetic. Okay? This was obtained by Monte Carlo simulation. Okay? So the funny part is this one is a little bit suspect. It's correct, but this one is not the lower bound. By the way, this gap is 0 in practice. That's just 0. Right? 78 minus that's 10. 10 divided by 70, that's 14%. You divide by 2, that's 7%. Right? And by the way, it's a very sophisticated controller. What the controller is V is quadratic. So you have 10 different quadratics, and your control is basically the maximum of 10 quadratics at each point. So you have a quadratic decomposition, right? Partition. You have a quadratic partition of R10, right? And then, so there are these quadratic surfaces, and in each one, you choose one of the 10 inputs, right? It's quite a sophisticated controller, right? And it was synthesized on a boat in about 15 minutes. So, okay. All right, so I'll finish up. So here are the points. Ляпунов's methods, they apply to much more than just stability theory. And besides stability theory, I think is mostly useless, in fact. I mean, you start with stability theory, but then you move on quickly to actually computing things with numbers and real bounds and things like that. The claim is this: if you take convex optimization puts computational teeth into Ляпунов's methods. It means it's that you can actually do this. It becomes actionable. It's something you can actually do. And the combination is very powerful and expressive, and it's weird. It's both theoretical, but it's also super duper applied. So I love things like that because they confuse everybody, right? The practical people say that makes sense to me. The theoretical people this makes them very uncomfortable. All these kinds of things, right? Because you know why. Okay, I already said that. So my claim is that this should be universally taught. This is how it should be taught. I haven't done it yet, but maybe I will sometime. And I mean, this is obvious, but so. And by the way, this is not to say that I had anything to do with any of these things, except that there's hundreds of references in these books that would tell you who really did do these things. So that would give you the history of these things. So don't take it that way. But okay, all right, we'll quit.
Okay, maybe there are some questions.
Oh, we're going to do questions now.
No, the questions outside will be about your life, but here about Ляпунов.
Tell me a brief story. How the CVX project had been started and how it was developed.
So my group has made things like CVX for 25 years. There were these weird ones we originally did using things like IAC and Lex, if you know what these are. So IAC is yet another compiler. And Lex is a lexicographic parser generator. So we wrote ones, and we just did the minimum amount so we could actually do controls with them. And then after a while, actually a guy from Sweden, made Hjalmar, if you know about this. And we looked at that and we said, yeah, that's the right thing to do. But then we didn't like it, so we did this. Right. And there's new one, and there's all sorts of other things coming as well. So, I mean, because MATLAB makes it a kind of a joke for people who do real stuff, right? Everyone here knows that, right? Is that not? Okay, so, yeah, so you know, if you go to a place that does real high-tech stuff, and you say MATLAB, they fall down laughing. And they say, thank you very much, and they send you away. If you go to Google and say MATLAB, they'll just fall down laughing. So it's not real. It's a fake language, right? But real languages are things like C++, Java, Python, that's a real language. Ruby, Scala, these are, okay, so, anyway, so there are versions coming up to speed in these other languages. Hopefully, yes.
Are there any developers besides you?
Yeah, but I know that a whole bunch have been developed inside companies because MATLAB is a joke for them. No, unfortunately. Some are open source and things like that. So I'm hoping this will happen. Maybe something in Python or C++. Who knows what will happen? But actually, what's great about it is modern languages are so powerful and expressive mathematically that it's like 3 lines to make a parser, right? So you can even write something that has CVX-like functionality. If you know these high-level languages well enough, you can write them in like 15 lines. So hopefully none of this has gotten to the, CVX is very well tested and things like that, but hopefully these others will be there. In a few years, I'm hoping these things will be there. And then it would be better if it wasn't even us who made it. That would be great.
Okay. More questions? Yeah.
Okay. You look just like the guy who just asked the question. Yes.
Where convex optimization methods are applied besides the Ляпунова area?
Oh my God. Everywhere. I hate to break it to you, but this. We think of like LMIs, you know, that's a tiny little thing like this in the world. It's used in, it's essentially, it's almost all of machine learning.
Mistake. LMI method besides the Ляпунова.
Oh, LMI. Well, I don't know, LMI. That's an old-fashioned term. We don't really use that anymore. But people who solve semi-definite programs and things like that, they do this in quantum mechanics, in chemistry now. I don't fully understand what they do, but they do something with them. And you do it in finance too, although that's a small thing. You meant semi-definite program. Oh, combinatorial optimization. That's one. Sure.
By the way, Ляпунов himself had never wrote Ляпунов equation.
Oh, he didn't?
No, he didn't.
Well, okay.
If you look at his dissertation,
Right.
there is no Ляпунov equation given in matrix form. No, it happened just at 50s, 1950s, that people recognized that it can be formulated in by guys like Malkin and others, but not Ляпунов himself.
Okay.
So
All right. So that part was on.
but it's fair that
That's the idea. Yeah.
Okay. Yeah.
Yeah.
One theoretical question. When we find in stochastic control, find the solution of the Bellman equation, doesn't it mean that the solution is optimal not only in the class of control policies like mu of x,
Yeah.
but it's optimal?
Yeah, in a much broader class. It's actually optimal in all policies which are potentially time varying and which are causal, which actually use all past information.
Yeah, thank you.
Yeah.
Okay. I don't see any more hands. So, okay.